Hello, everyone. Welcome to Physics 205. So in this lecture video, I want to talk about rotational motion of solid objects, which are also called rigid bodies. So this is a little bit different than circular motion. Circular motion was the motion of a particle or an object that you can consider to be a particle moving in a circle. This is actually the motion of an extended object, like some type of a wheel or a baseball bat, some type of extended object that's rotating about some axis of rotation. Okay, so it's a little bit different than circular motion. Now, the first thing I want to talk about is kinematics of rigid bodies. So, in other words, we'll discuss the motion without regard to what's causing the motion. So in this case, it would be the torques that cause the rotational motion. So we're going to ignore torques. We'll get into that in the second part. So we're just going to look at the motion itself. All right, we need to talk about a few definitions first. So the first definition is something called rotational displacement. So rotational or angular, I'll use those two words kind of interchangeably. I'll often sometimes just call it angular displacement. First of all, it's denoted as delta theta, so change in theta. It's a quantity representing how far an object has rotated. Now, it can be measured in several different units. You could measure in degrees. You can measure it in revolutions, like the number of times it went around, how many revolutions, or you can measure it in radians. Now, the most common unit of measure is radians, although we'll occasionally use revolutions as well. But typically, we'll use radians. Okay, so that's the most common measure for rotational displacement. Now, to compute it, to figure out that delta theta, it's simply equal to the final angular position minus the initial angular position. So you can think of it as theta final minus theta initial. This is analogous to when we were talking about one-dimensional motion, right? When we had delta x, like the change in position was the final x final minus x initial, final position minus initial position. It's exactly the same thing. It's analogous, except instead of linear positions, we're talking about angular motion. Okay, so it's a change in angle instead of a change in position. Okay, to remind you, remember the definition of an angle in radians. So if I want to measure this angle here, this theta in radians, it's defined to be the length of this arc, which is like part of the circle, that arc length, so which you usually call S, divided by the radius. So theta in radians is the arc length, S, divided by the radius. Now notice here that these two variables here, the arc length and the radius, are going to be measured in some units of length, right? Let's say meters. So if the arc length is measured in meters and the radius is in meters, those units are going to cancel. So the angle here, theta here, is not going to have any units. Now we usually write radians to remind ourselves it's in radians, but it's really unitless when you're measuring in radians because the units of length cancel. Okay. Now, if you do, let's say we do a full rotation, like you have a circle here and we go all the way around once, right? One complete rotation. In that case, if we want to know the angle in radians, well, the arc length is going to be this entire distance around the circle. And we know that's simply the circumference, right? And remember, the circumference is equal to 2 pi r. So it would be the circumference divided by r in the bottom. So we have 2 pi r, I have it done here, divided by r. The r's cancel. So the angle in radians is going to be 2 pi. So one full rotation, if you go all the way around in a circle, that's equal to 2 pi radians. Okay, well, we also know in degrees, right? One rotation is 360 degrees, and you can also write it as one revolution. So these are all equivalent. So these will give us some conversion factors. If we need to go between, revolutions and radians or degrees and radians, we have these conversion factors here. So 360 degrees is equal to one revolution, which is equal to 2 pi radians. Okay, so actually the first example is just a simple conversion problem. Let's say we have a tire and it undergoes 3.5 revolutions. Okay, so it rotates 3.5 times, right, around its axle. What is the angular displacement in radians? Okay, well, we know the angular displacement in revolutions is 3.5, right? That's what they're giving us. So we need to convert that to radians. Okay, well, using our unit conversion factor here, right? Or I should say using our relationship here, we can create a unit conversion factor. We know that 2 pi radians is equivalent to 1 revolution. So I can either write that fraction as 2 pi radians over 1 revolution or the other way around, 1 revolution over 2 pi radians, right? Remember back when we talked a lot about conversions near the beginning of the semester? So the question is, which unit conversion factor do I want to use? Well, I want revolutions to cancel, so I better put the revolutions in the denominator for my unit conversion factor and radians in my numerator because I want it to survive in the answer here. So if I multiply 3.5 revolutions times 2 pi radians over 1 revolution, I'm going to get 21.99 radians. I'm going to round that to the sig figs, say 2 sig figs. So that gives me around 22 radians, okay? So often you will have to convert between revolutions and radians or radians and revolutions. Sometimes you can leave the answer in revolutions. That will be fine. It just depends on what's being asked for in the answer. But sometimes you have to do these conversions. So again, as long as you remember this, 360 degrees is equal to 1 revolution, which is equal to 2 pi radians, then you can do any of those conversions. Okay, another definition. So that was angular displacement. Next definition is angular velocity, which we usually denote as omega here, this Greek letter omega. So angular velocity is the rate of change of angular displacement. Just like, again, this is analogous to the linear situation. Remember we said velocity, average velocity, is the rate of change of position. So if this were just velocity, average velocity, it would be delta x over delta t. But in this case, we have angular velocity, and it's the average. Really, technically, it's going to be the average angular velocity is the change in angular displacement, or I should say the change in angular position, which is the angular displacement, divided by the change in time. So again, it's analogous to the linear situation where V_av would be delta x over delta t. Omega_av is delta theta over delta t. So it's a change in angular position, which is the angular displacement, divided by the change in time. And that's in radians per second, or you could also, if you want to leave the angular displacement in revolutions, you could write it as revolutions per second. Depends on what the question's asking for, okay? Now, if you wanted the instantaneous angular velocity, then you would shrink this time interval so it's getting smaller and smaller and smaller and going towards 0, okay? So this is like the average angular velocity, which is mostly what we're going to deal with in this course. So that's angular velocity. Then angular acceleration, which we denote by the Greek letter alpha here, so it's kind of like an A in alpha, that's simply the rate of change of angular velocity. So again, this is analogous to linear acceleration. Remember, if we had AAV, linear acceleration, that was a change in velocity over change in time. Now we're talking about angular acceleration. So the average angular acceleration is the change in angular velocity over change in time. And in those units, it'd be radians per second, which you can write as radians per second squared, or revolutions per second squared. Okay, so these are all analogous to what we had when we talked about linear motion, except now we're talking about angular motion. Okay, one of the applications that's going to come up here is, what if we have problems, so applied problems, where we have constant angular acceleration, right, or constant rotational acceleration? Well, we went through all of this again when we were talking about linear motion. We did a whole section on equations where we had constant linear acceleration, right? Constant ax or constant ay. Same thing here. So now let's say we have a constant alpha. Well, if the angular acceleration is constant, then we can derive rotational kinematic equations that are analogous to what we had for our linear acceleration equations. So, and I have them written down here. So just to remind you of the linear equation that we derived earlier in the course. So average velocity, V_av, is delta x, right? Change in position, which is called the displacement, or you can think of it as linear displacement, divided by change in time. As long as the acceleration, the ax is constant, so if the ax is constant, then remember the average velocity is simply the average of the initial and final velocities. So you can write it as v initial x plus vx over 2, right? This is the initial velocity, that's the final velocity. Again, this is all review, right? We should know all these equations. The final velocity, Vx, is equal to the initial velocity in the x direction, v naught x, plus the acceleration in the x direction times delta t, right? That was one of our constant acceleration kinematic equations. Another one was that the change in position, the displacement in the x direction, is equal to the initial velocity in x times delta t plus 1/2 ax delta t squared, right? We had derived that earlier in the class. And then we had this other equation that doesn't involve time. So the final velocity squared is equal to the initial velocity squared plus 2a, right, acceleration times the displacement times delta x. So we just said, well, the angular situation is analogous, right, to this. So basically what we're doing is we're replacing the velocity by omega, by angular velocity. We're replacing x by theta, right? The position, the linear position, is replaced by the angular position. We replace, again, this is v by omega, right? So linear velocity by angular velocity. And then the other replacement is the linear acceleration, ax, would be replaced by alpha, by the angular acceleration. And notice that these equations look exactly the same, right? So for angular situation, the average angular velocity is equal to the angular displacement divided by the change in time. Or you could write it as the average of the initial and final angular velocities, right? That's analogous to what we did here. Then I have an equation if I want to find, so if I just write omega by itself, that means the final angular velocity is equal to the initial angular velocity plus the angular acceleration times delta t. That's analogous to this equation. If I want the angular displacement, it's equal to the initial angular velocity times delta t plus 1/2 angular acceleration times delta t squared. Again, that's analogous to what we had here for the linear case. And then finally, if I don't want to include the delta t, I can derive this other equation that just involves the angular velocities, the angular acceleration, and the angular displacement. So again, that's analogous to this one, right? So in this case, the final angular velocity equals the initial angular velocity, or final angular velocity squared equals initial angular velocity squared plus 2 times angular acceleration times the angular displacement. Okay, again, analogous to this. So the same type of problems we did here with the linear case, we can also solve with the angular or rotational case. And that's how you should remember them. Just replace v by omega, x by theta, and then ax by alpha here. And you'll have exactly the same equations. Okay, so let's do a couple of problems, and then I will come back to this and we'll talk a little bit about the dynamics of rigid bodies, where we actually look at now the causes of the motion, which is basically the torques. So let's look at these. I'll jump on the iPad and we'll do these two problems first, then we'll get into the dynamics. Okay, so in this problem, I'm told a cyclist starts from rest and pedals so that the wheels make 8.0 revolutions in the first 5.0 seconds. What is the angular acceleration of the wheels? And we're assuming that the angular acceleration is going to be constant. Okay, so what do I know? Let me write down what I know. I know that the angular displacement, because the wheel makes 8 revolutions, that delta theta is going to be 8 revolutions. Now, we might want to actually solve this in terms of radians. So I'm going to convert to radians first. So if I multiply, remember my unit conversion factor is there's 2 pi radians per 1 revolution. And I want to do that way because I want revolutions to cancel. And then I'll end up in radians, right? And it turns out in this case, it's like 50.27 radians. Okay, so that's my angular displacement, 50.27 radians. What else do we know? Well, we know the initial angular velocity is 0, right? Because it's starting at rest. So this is radians per second, 0 radians per second. We know that the time that it undergoes this rotation is 5, I guess it's 5 seconds. And let's see, and we're looking for the angular acceleration, or we're looking for alpha. Okay, we don't know what alpha is, so that's a question mark. All right, so if we look at our constant angular acceleration equations, is there any equation that involves all these variables where the only unknown is alpha? Yes, if you look at this one, right, remember we know that delta theta should equal omega naught delta t plus 1/2 alpha times delta t squared. Okay, and I know delta theta is 50.27. Omega naught was 0. Delta t is 5, although I don't even need it there, right, because it's going to be 0, plus 1/2, I don't know alpha, and again, this is 5.0 squared. Okay, so to solve this, what I can do, so this term is gone, right? That's just 0. I can multiply both sides by 2, just to get rid of that 1/2 on the right-hand side. So here, I'll do it out carefully. So if I multiply both sides by 2, right, the 2's will cancel on the right-hand side. Then if I divide by 5.0 squared, both sides, that'll give me alpha. So then if I solve this, right, that cancels, I'm going to get alpha is equal to, and if we work this out, it's around 4 point, I guess, let's see, I guess I want maybe 2 sig figs, right? So 4.0 radians per second squared. So that would be my angular acceleration, 4.0 radians per second squared. Okay, another problem. In this problem, you're told a bicycle wheel is rotationally accelerated at the constant rate of 1.2 revolutions per second squared. If it starts at rest, what is its rotational velocity after 4 seconds? And through how many revolutions does it turn in this time, right, in the 4 seconds? Okay, so again, what do we know? We know, so this is part A first. We know that alpha is 1.2 revolutions per second squared. Now, if I wanted to, I could convert that to radians per second squared, right? I could write my alpha, my angular acceleration in radians per second squared. I'm going to leave it in revolutions in this case. So that means my velocity will be in revolutions per second, and the number of revolutions, actually part B is asking for a number of revolutions. So I'll just leave it in revolutions per second squared, and it'll just be easier. Okay, what else do we know? It starts at rest, right? So we know that omega naught is equal to 0 revolutions per second, or radians per second, right? It's going to be 0 for both. And then the time, delta t, is 4 seconds, right? 4.0 seconds. Okay, so I want to find the rotational velocity after 4 seconds. So I really want to find like the final rotational velocity. So if I use this equation, I know that omega, right, that means the final angular velocity is equal to the initial angular velocity plus alpha delta t. So in this case, omega is going to be, this is 0, right, plus 1.2 times 4. And if you work that out, you're going to get 4.8. And in units, remember, we left it in revolutions per second. So the final rotational velocity after 4 seconds is 4.8 revolutions per second. And then for this part B, it says through how many revolutions does it turn in this time? Okay, so really, if we're looking for delta theta, right, we want to know what that is, and we want it in revolutions. We want our units to be revolutions. So as long as we leave everything else in revolutions, it'll come out correctly in revolutions. So again, if we look at our equations, it looks like this one will work. Delta theta is equal to omega naught delta t plus 1/2 alpha delta t squared. So delta theta is going to be, this is 0, right, times 4 plus 1/2. Alpha is 1.2, right? And it's revolutions per second squared. So again, we'll end up, our answer will be correctly in revolutions, times 4 squared. And if you work that out, it turns out it's around 9.6 revolutions. So in this case, this bicycle wheel rotated around 9.6 times, right? 9.6 complete rotations, basically. Okay, great. So let's go back now and talk a little bit about rotational dynamics, where now we look at the cause of the motion, which is going to be the torques. Okay, so dynamics of rigid bodies. So again, now we need a few more definitions here. So one of them is called the rotational inertia, or a more common name is the moment of inertia of some extended body, some rigid body, some object. So the moment of inertia basically provides a resistance to changes in rotational motion. And it depends on the distribution of the mass about the axis of rotation. If the mass is further away, then the moment of inertia will be larger. If the mass is distributed such that it's closer to the axis of rotation, then the moment of inertia will be smaller. Okay, so how do we compute the moment of inertia? Well, let's say we have this object, right? So here's my object, this blob right here. So this is some like rigid body, right? It's made up of a bunch of particles here. And each of those particles you can think of as having a mass. So like I just drew a few of them here, but this is like M1, mass 1, mass 2, mass 3, all the way up to mass n. But think of it, the whole thing being filled, right, with all these little particles. And each one of these little bits of mass here are at a certain distance away from this is the axis of rotation. So this thing would, if it rotated, would rotate about this point right here. So each little bit of mass is a certain distance away. So like M1 is this distance L1 away from the axis of rotation. M2 is this distance L2 away from the axis of rotation. M3 is this distance L3 away, and so on. And Mn is Ln away. If you want to calculate the moment of inertia of this object about this point, then what you have to do is you have to sum each little bit of mass times its distance squared from that rotation point. So if I do m1 times L1 squared plus m2 times L2 squared plus, and this dot, dot, dot means do all these masses here, all the way up to mn times Ln squared, that is going to give me my moment of inertia, which I'm calling I. All right, so that's how theoretically you would calculate I. Now you can also, if you want to make this notation more efficient here, you can use the sigma notation. Remember, sigma means the sum. So you would read this as the sum as I goes from 1 to n of MILI squared, right? So the I here, these subscripts go from 1 to n, right? So basically you're writing this thing over again, but in this more efficient notation using sigma. Now, because it's a mass times a distance squared, the units for the moment of inertia are kilograms times meters squared. Okay. Now, typically, so that, again, this is the theoretical definition. Typically, you have simple shapes like a disc or a ring or a rod. And then the moment of inertia is given by a simple formula that involves the mass of the disc and the radius of the disc, or the mass of the rod and radius of the rod. Okay, but for our cases, in most cases, I will give you what this moment of inertia is. So you don't have to worry too much about this. Just remember that the moment of inertia depends on the distribution of the mass about the point of rotation. Okay, so that's important. Actually, here's one example. Let me jump on the iPad for a second. Let me show you the difference. If you have a ping pong paddle and you calculate the moment of inertia about two different points. Okay, so let's say I have these two ping pong paddles. So I have a ping pong paddle, and one of them, I decide to calculate the moment of inertia about this point in the handle here. So that's my axis of rotation right in the handle. In the second example, let's say I have the same ping pong paddle. Let me see if I can draw this similarly. So assume this is the same ping pong paddle, But now I'm calculating the moment of inertia about this point in the paddle itself. So that's my axis of rotation. So the question is, in which case, the left case or the right case, do I have a larger moment of inertia? So if I were to compare, let's call this one I1 and call this one I2. Which case do I have the larger moment of inertia? Okay, so if you think about this, right, in the first case, most of my mass is out here, right? There's a little bit here, but most of it is out here. And notice that these distances are pretty large, right? They're far away from the rotation point, from the axis of rotation. And remember, moment of inertia depends on each a little bit of mass times its distance squared from that rotation point. Whereas in the second case here, it's the same total mass, right? It's the same ping pong paddle, so it has the same total mass, but the way the mass is distributed, because I'm calculating about this point right here, is this mass is on average closer. There's some that's far away, but most of it is closer to the axis of rotation, so they're going to have smaller values for those distances. And again, to calculate moment of inertia, it's a little bit of mass times this distance squared. Well, that's going to be a much smaller value than like this mass times this distance squared, right? Because it's a much larger distance. So same mass, but it's distributed differently. So it turns out in this case that the left example is going to have a larger, right, moment of inertia. So that's what I mean by the moment of inertia depends on the distribution of the mass about the point of rotation. Okay, let's go back to the handout. Okay, so remember, the whole point of rotational dynamics is now to look at the causes of the motion, right? The causes of the rotation. And it turns out that it's the torques. If there's any torques applied to the rigid body, that's going to cause the rigid body to rotate. So you guys remember Newton's second law, right? For linear motion, that's simply that the sum of the forces is equal to mass times acceleration, right? F equals ma. It's really F net equals ma. So sum of the forces equals mass times acceleration. Well, it turns out for angular motion or rotational motion, there's an analogous formula. And you might ask yourself, okay, what's the analogous formula? Well, it turns out it's a sum of the torques, or the net torque is equal to I times alpha, moment of inertia times angular acceleration. And notice that these things are analogous, right? They correspond to one another. So you might ask yourself, okay, what is an analogous quantity for force, but for rotations? Well, that's got to be the torques, right? Torque is sort of like a rotational force. What's an analogous quantity for linear acceleration, but for rotations? Well, that's going to be angular acceleration, right? Instead of meters per second squared, it's radians per second squared, or revolutions per second squared. And then what's analogous for masses, right? That would be the linear case. But for rotations, it turns out that is the moment of inertia. That's the I. So another way of thinking about the moment of inertia, I, it's sort of like a rotational mass. Okay, so I is like a rotational mass. Whereas masses resist changes in linear motion, right? If you have a larger mass, it's harder to accelerate the object. Moment of inertia, the I, resists changes in rotational motion. So if you have a larger I, then it's harder to rotate the object. Like that ping pong paddle where we calculated about the handle, right? It would be harder to rotate that than to rotate the other one where we calculated about the paddle itself. Okay, so this formula is very similar to what we knew before, except instead of forces, I have torques. Instead of accelerations, I have angular accelerations. Instead of mass, I'm going to put in the moment of inertia. Right, so these are analogous formulas, and it helps you remember. This is sort of like Newton's second law for rotations. That's one way of thinking about it. Okay, so given that, let's finish up here with a few examples, and I'll jump over to the iPad to do these. Okay, so we'll start off with a very straightforward example. This first example says a net torque of 60 Newton meters is applied to a disc which has a rotational inertia of 12.0 kilograms per meter squared. What is the rotational acceleration or angular acceleration of the disk? Okay, so they're giving us, right? They're telling us that the sum of the torques, which is the net torque. Remember, sum is the same. If I add up all the torques, I get the net torque. That's equal to 60, right? Newton meters. Is applied to a disk which has a rotational inertia. So it's saying that the rotational inertia, which is the moment of inertia, another name for moment of inertia, I, is 12.0 kilograms times meters squared. And we want to figure out the rotational or angular acceleration. We want to figure out alpha. Well, we know that the net torque is equal to I times alpha, right? Or the sum of the torques is equal to I times alpha. We just learned that. So I can solve this equation for alpha by dividing both sides by I. So these I's cancel, and I'm going to find that alpha is simply going to be the net torque divided by I. So in this case, the net torque was 60 divided by I, which is 12. And I'm going to get 5.0 radians per second squared. Okay, so basically to solve this problem, we just plugged into Newton's second law for rotations, right? The fact that the sum of the torques or the net torque equals I times alpha. Remember, this equation can also be written as the sum of the torques equals I times alpha, right? It's the same thing as net torque equals I times alpha. Okay, so that was straightforward. Next question. So now you're told a torque of 60 Newton meters producing a counterclockwise rotation is applied to a wheel about its axle. A clockwise frictional torque of 10 Newton meters also acts on the axle. So we have this like wheel here. We have this wheel. Just draw some spokes in here. And we have I'll just draw it as an arrow. We have a counterclockwise torque of 60 Newton meters. And then because of friction, we have a clockwise torque that's resisting the motion of 10 Newton meters. Okay. And then there's a couple of questions. So the first question is, what is the net torque about the axle of the wheel? And then the second question is, if the wheel is observed to accelerate at the rate of 2 radians per second squared under the influence of these torques, what is the moment inertia of the wheel? Okay, so part A, what is the net torque about the axle of the wheel? Well, remember, the net torque is simply the sum of the torques. And now the sign is going to be important, right? Remember, if it's counterclockwise, so counterclockwise, let me spell that again. That is defined to be positive, okay, just by agreement. And then clockwise is negative. So the net torque is going to be the sum of the torques, which is a positive 60. I'll just write a plus to emphasize it's positive because it's counterclockwise. And then the other one is going to be plus a negative 10, or I could just write it as minus 10, right? Because that's clockwise. That frictional torque is clockwise. And then if you work that out, of course, that's going to be 50 Newton meters. So the net torque is a positive 50 Newton meters. So I still have this like counterclockwise net torque, right, of 50 Newton meters. And then for the second part of the question, it says if the wheel is observed to accelerate at the rate of 2 radians per second squared, so they're telling us alpha now is 2 radians per second squared. What is the moment inertia of the wheel? So we're looking for I. Okay, so again, we're just going to use Newton's second law for rotations, right? Because we know the net torque and that's got to equal I times alpha. So if I solve this for I divide both sides by alpha, right? It's going to be the net torque divided by alpha. So if I work this out, this will be 50 divided by 2. Let's assume it's like 2.0, so it has like 2 sig figs. So that's going to be 25 kilograms times meters squared, right? That would be my moment of inertia in that case. Okay, let's do one last problem here. So now we're told a merry-go-round has a moment of inertia of 200 kilogram meters squared. So that's going to be I, right? I is equal to 200 kilogram meters squared. Assume a person can apply a constant net torque of 50 Newton meters on the merry-go-round for 5 seconds. Okay, so the net torque is going to be 50 Newton meters. And then the time, they're applying it for a time of 5 seconds. If that merry-go-round starts at rest, so that means omega naught equals 0. What is its rotational speed after 5 seconds? So now I want to know what is omega. I could write it this way. I'll just say omega at 5 seconds. We want to know that. And then what is the angular displacement after 5 seconds? So what angular displacement did the merry-go-round undergo in 5 seconds? So I'm looking for delta theta, right? Also in 5 seconds. Okay, well, in order to answer those questions, which involve the kinematic equations, right, for rotation, I need to know alpha. I need to know the angular acceleration. And then I can use my kinematic equations for rotation, and I can answer these questions. So how do I figure out alpha? Well, to figure out alpha, I can use Newton's second law for rotation, right? Because I know the net torque, I know the moment of inertia. So again, tau net is equal to I times alpha. So if I divide both sides by I, that'll cancel, and that'll give me alpha, right? So alpha in this case is going to be 50. So it'll be the net torque divided by I. So it'll be 50 divided by 200, which is going to be 0.25 radians per second squared. So I know alpha now. Okay, what am I looking for? Well, the first question, I'm looking for the rotational speed, right, which is rotation velocity after 5 seconds, and it's starting at rest. Well, if I go to my kinematic equations, remember one of them is that omega is equal to omega naught plus alpha times delta t. And that will work, right? So omega naught, it's starting at rest, so that's 0. Alpha we just found was 0.25. And then we want to calculate this for after 5 seconds. So it looks like the angular speed or angular velocity after 5 seconds is going to be 1.25 radians per second. And if I assume that 5 is 5.0, this is really 5.0, then really this is like 2 sig figs. So if we're being very careful, this should be 1.3, right, radians per second. Okay, and then finally, what angular displacement did the merry-go-round undergo in 5 seconds? Well, again, I can use my kinematic equations, and now I'm trying to find delta theta. Remember, that's equal to omega naught delta t plus 1/2 alpha delta t squared. So again, if I plug in, this is 0, right? Starting at rest. This is for 5 seconds. 1/2 alpha was 0.25, and then this is 5.0 squared. If you work that out, you're going to get 3.125 radians. So again, if I round, let's say 3.1 radians. Okay, so now I know that this wheel underwent a rotation of 3.1 radians, right, in the 5 seconds. Not very far, right? But obviously, it kind of makes sense, right? A large merry-go-round would be tough to get started to get it to rotate. If you want to know how many rotations or like revolutions this is, you could convert it, right? So I could take 3.1 radians and multiply. Now I want to use the fact that one revolution, so I need that in the numerator, is equal to 2 pi radians in the denominator. So radians cancels. And if you work that out, it's around a half of a revolution. So the whole merry-go-round maybe rotates around halfway around in 5 seconds, given this information, given this moment of inertia, and given the torque that the person is exerting on the merry-go-round. Okay, so that's really all I want to talk about for rotational motion of objects and rigid bodies. Just kind of touched upon it. Great, thank you.